Tyson.
Okay. Everybody talk about geotech needs to settle down. All right.
We do, but
I'm such a dork.
I told Dr. Na that you told our capstone group that we don't need to consider long-term consolidation. And he says, that's what he means, he's just a structural engineer.
You're right, okay. Hey, so my responsibility ends about right here. I'm kidding, you know, but I thought he'd get a kick out of that. I did take some advanced foundation design classes in grad school. I really enjoyed them, but you know, that was really early, and then I just went into structures land. Been doing that ever since. Okay, let's get started. Yes. I started from the foundation up. Yes. Okay. All the outstanding homework should be graded. Homework 6.5 is due today. I want to make sure that everybody is clear that I'm assigning a homework today that is due Friday, and I am assigning a homework Friday that is due Monday, okay? I am assigning one, okay? But we are not going to have an in-class lecture on Friday because of the Virginia's conference. I'm going to be, so everybody's going to be at, or most of the people here are going to be at beach for setting up, or there for the canoe race. I'm going to be here on campus because I'm setting up the helping set up the steel bridge competition, which is taking place on Saturday. So I'll be sticking around here and getting all that sorted. So we do not have an in-class lecture on Friday. Now, I have already recorded that lecture, and it's on the YouTube playlist, and I set it as a premiere. You tell me, do you want me to go ahead and make it live after this, or do you want me to?
Yes.
Okay, I'll make it live. All right, I'll do that. As soon as I get around to it, I'll just make it public, and then it'll be live. So I do that in case, like, if I forget, then at least it goes live when it's supposed to. Yes, sir.
Will you make the homework live as well?
The homework
Due Monday.
I can do that.
Okay.
It's already posted, so if you want me to turn that on too, I will. Sure. I'll do that. You got it. So
Thank you.
absolutely. But I'll make it due Monday.
Okay.
So this homework will be due Friday, that one will be due Monday. If you want to get them both done and knock them both out, that's great. So, okay. All right. So today, what we're going to do is discuss design of discretely braced beams. And I will tell you that the process is generally the same, except for the step where you actually pick your trial shape. In the past, for continuously braced beams, our tool for selecting the shape was table 3.2. Now the tool is table 3.10. So it's the same process, it's just a different selection strategy. So we're going to do an example problem today, and you're going to see how it is remarkably similar to what we have done before, except for that stuff in the middle. Now, our example today is what I'm calling a low CB value example, okay? So we have a low CB value example and we have a high CB value example. And the difference between the two, so those terms are my terms, those are like my verbs or adjectives for the examples. But the difference, like what defines the difference will become clear as you get into the examples. Basically, high CB values cause you to iterate your selections a little more than with low CB values. So let's make sure that we're clear on the equations for capacity. So we have zone 1, zone 2, and zone 3. One thing I will tell you, and I think I actually mentioned this in the pre-recorded video, but so if you are given a beam and you need to analyze that beam, it could be either zone 1, zone 2, or zone 3. You really don't know until you go through the math and see. But I will tell you that in the land of design, when you as the engineer are responsible for selecting optimal economic shapes, you will most likely be in zone 2. Okay, that will most likely be where you're going to land if you're in design mode of discretely braced beams. So of the two, and I'm not really counting zone 1 because that's just P and P, but But of the two, which do I think you need to be more comfortable with in design mode? This one, okay? So just throwing that out there. Okay, now let's make sure that we're all comfortable with table 310. I got my little animation slide here to show you how this works. So again, whenever you're using, table 310. Whenever you're in table 310, you take your factored moment and you divide out the effects of CV so that you're entering the table with an effective CV value of 1, because that's where these charts are configured from. They assume a CV value of 1. We then look for the point where the x-axis corresponds to whatever unbraced length we're considering, and the y-axis corresponds to whatever moment that we need to design for, divided out the effects of CV. We look up to the right and we find the first solid shape. So last time what we had done is we just did a couple of examples. So we find a point, we recognize that anything in the blue shaded region is a safe selection. And so we draw up and to the right, and we find the first solid line segment that we could deal with, or that we should consider, in which case that's a W27 by 146. Okay, so that is sort of the process for selecting a shape. Now I want to get into the design aspect. How do we actually design a discretely braced beam? And honestly, I don't really think there's anything in these slides that you probably couldn't come up with on your own based on what we already need to do for continuously braced beams. Because remember, we have 3 limit states that we need to assess. We need to ensure that our selection has adequate moment capacity. We need to ensure that it has adequate shear capacity. And we need to ensure that it meets any associated deflection requirements. So it's the same story here, okay? So what do? Well, the first thing that we need to do is we need to compute a factored moment, okay? So we compute a factored moment, but in our analysis step, we probably also ought to compute a CV value. So that's a little new. We didn't have to do that for continuously braced beams because we didn't care about CV. That didn't really matter, okay? CV only affects the lateral torsional buckling capacity, and since in continuously braced beams we don't have to worry about that, no big deal. So in step 1, we're basically performing our structural analysis. If we're not given a beam self-weight, we should assume one. Somewhere between 50 to 100 pounds per foot, I think, is pretty common for most structural engineering applications. And I think you'll get better at that the more that you design beams to be able to pick a value that makes sense. Usually what I kind of do is, so if you look at framing plans, floor framing plans, the beams frame into the girders. So the girders are the larger elements that have usually longer spans and larger tributary areas. So like what I might do if I would, for most typical building frames is I might say, how about 50 pounds per foot for the beams and 100 pounds per foot for the girders, something like that. That's a very, very elementary assumption, but it's somewhat based in reality given the changes in tributary area. But you'll just get better at that with experience. The next thing that you need to do is the other aspect of the structural analysis is to compute the required moments of inertia for any deflection requirements. So sort of like step 1 is assessing all of your strength limit states, and step 2 is assessing your service limit states. So after these 2 steps, you should have really 3 values that you need for design. Now you will end these steps with more values, like you'll have a factored shear and things like that, but really what you need to be considering for design is MU, a CB value, and a moment of inertia that's required. That's what you should be ending these first 2 steps with, are these 3 quantities, okay? Now what you do after that is you go into table 310 with this on your x-axis and this on your y-axis, and you pick a section, okay? Now, the thing is, keep in mind that we can only use table 310 if Fy is 50 KSI, but again, that's not going to be a problem for most rolled shapes. I just want to point that out. I think in the last edition of the manual, you can actually download table 310 if you had Fy 65 KSI. I know there were some design aids that you can download for 65 KSI. I can't remember if table 310 was part of it. But again, if you have your AISC account, which I believe everybody in here does to get your manual, again, there's a lot of really cool and really free resources on AISC that you should consider downloading. Once you get a trial section, you should verify that the moment of inertia is good enough. If not, select based on 3.3. Yes, sir.
Do those resources go away when you graduate?
So what I would say is probably, But I don't, like, what I don't know is, I don't know how long your student account is active. So like, I know for me, like, I have an educator account, and so like what'll happen with me is, you know, I think I have to periodically verify that yes, I'm still an educator, and so on and so forth. So like for me, if I went and, you know, left Marshall and went into private practice, then I wouldn't be using my EDU email address and all that. So what I would suggest though is go ahead and download all that stuff now. So, but I'll also say that if you're at a firm or a place that does a lot of steel design, they will probably pay for, you know, an AISE account, then it wouldn't matter anyways. So I just think it's good to have a lot of this stuff. Like, as an example, there's a really, really cool design guide for torsion, and it's a lot of theory based. I don't think a lot of it's really going to change all that much from spec to spec. So, okay. Now, the last thing that you want to do is, okay, so let me go back to this. So you're going into table 310 and selecting a shape. Before you do all your analysis, you should verify that it has a high enough moment of inertia. If it doesn't, skip all this table 310 stuff and just go to those moment of inertia charts and pick a shape. That just means that the shape isn't governed by strength limit states, it's governed by deflection. Using table 310 assumes that the beam's capacity is going to be governed, or the beam's design is going to be governed by its moment capacity. And if this isn't going to work, then all that doesn't, you know, all that isn't really going to influence your selection. Now, once you have a trial shape, you need to analyze it. And what I would say is that unlike continuously braced beam design, analyzing the beam is highly, highly necessary. With continuously braced beams, as long as your self-weight was assumed correctly, you could probably, I don't want to say you could skip this step, but with enough experience, you can sort of see that this is a formality. But with discretely braced beams, I don't think this is a formality. I think this is incredibly, incredibly important. And what I'm saying about discretely braced beam design is that if you are designing a beam with a high CB value, and I'm using that in quotation marks, high CB value, it can generate a false positive. You can select a section from table 310 that looks like it's going to work and it doesn't. So analyzing is incredibly important, okay? Maybe we'll talk a little bit about that today if we have time. The shear capacity, make sure that you check that. Right now, we're just looking it up. On Monday, we're going to discuss how to actually compute shear capacity. Because this whole time, we've been just relying and hoping that table 3.2 works, and I think that you should be armed with at least a little bit of information to understand how to compute it. It's not hard. In most cases, it's just the area of the web times 0.6 times Fy. But I want you to understand all of the aspects that can go into it. And finally, making sure that you've got your deflection limits satisfied. One final tip regarding table 310. This is just one of those like Dr. Mike's tips and tricks. Sometimes when you're using table 310, like the lines kind of get bunched up, and if you're trying to pick one, it might be kind of hard to see which one to pick. So I kind of suggest sometimes that maybe what you ought to do is find that point and just trace upwards and find the first section that you intersect with. Sometimes what you might find is that you're tracing upwards and you can't actually see the shape, and you actually need to turn to another chart to find the shape that works. So that won't happen on like the FE exam because they only give you one page, so the problems will be designed such that you'll be able to find the section on that one chart. But in real-life steel design, you might need to go to the next page of table 310 to find the shape that works. And sometimes when the lines get like this, tracing upward might be a little easier to see the shape that works. Make sense? Let's do a problem. Okay, so I've got a discretely braced beam that I want to go through with you all today. And like I said, I think we'll have maybe a little bit of time to look at high CV values in a bit to kind of show you what happens there. We won't be able to get into the details, but maybe we'll be able to get into it a little bit. So let's design a discretely braced beam for the loading shown. So I have a dead load of 1 kip per foot and a live load of 3 kips per foot. The dead load shown does not include the beam self-weight. So what we would say from a terminology perspective is that this dead load is superimposed. Superimposed meaning that it is on top of the beam self-weight. The beam is 24 foot long, and we're going to be designing this beam assuming it's discretely braced. Specifically, that it's only braced at the ends, okay? We're going to be designing the beam for these loads and also to achieve a live, or to meet a live load deflection limit of L divided by 360. So this is going to be the focus of our design today. And this is, I would say, about as bread and butter a structural steel design problem as you could get in the real world. This is about as straightforward and real life as it could get. So 24 foot long beam. So imagine designing a beam in this building that's 24 foot long. There's the loads pick beam. That's pretty real world. Okay. So the first thing that we're going to do is do some structural analysis here. So let's do this. So step one, structural analysis. And while I'm working on this, do y'all need a few minutes or do you want me to hold off for, I mean, you tell me, am I good to go or you may wait? Okay, all right. So what we've got here is we've got a beam. So let's see if we can identify some aspects of this beam. Let's just make sure everybody's paying attention. So the beam is 24 foot long. What is LB for this beam? It's 24 feet. So in this case, the span length and the unbraced length are the same, okay? Just make sure that you're not always saying that. If there's a brace at mid-span, so if we had a brace here, then LB would be 12 feet. It wouldn't be 24 feet. So just make sure that you're not always saying that L equals LB. Okay. Now, we were given a dead load of 1 kip per foot, and we were given a assumed self-weight of 100 pounds per foot, or 0.1 kip per foot. Okay, so what I'll do is I'll make a big note here and say that's assumed. Okay, we have a live load of 3 kips per foot and the length is 24 feet. So we've got a couple values that we can go ahead and start computing. So we'll start off with, so here's how I'll handle this. I'll do the moment over here. So the dead load moment, and hopefully, like I'm just sort of going through this pretty quickly. I think at this point this should be pretty familiar. If not, if there's anything that you're having a hard time following with, let me know. But this is going to be the dead load plus the self weight times L squared over 8. And again, WL squared over 8 works because the beam is simply supported and the load is uniformly distributed. If we had a cantilever beam or point loads or anything like that, this would not work. We would have to use another method, or we'd have to just draw the shear and moment diagrams. So this is going to be, so what I'm going to do is I'm going to write this as 1.1 kips per foot. This is 24 feet squared over 8. And what do we got for that?
79.2.
79.2 foot kips. Do I have a second?
Mm-hmm.
Okay. And we'll go ahead and do the live load. The live load is WL, L squared over 8. So same calculation, just different load. And again, I know that this is probably not the most efficient way of doing this calculation, because we could just factor the load and just do WL squared over 8 once. But again, I kind of want you to get into this habit in case the live load moment is not uniformly distributed, in case it's a point load or something else. So what do we get for this?
216.
All right, second.
Yep.
All right, and so MU is 1.2 dead plus 1.6 live. And what is that? We'll write this out. It's 1.2. So what do we get for that?
440.64.
440.64. Do I have a second? Okay, so just to make sure everybody's awake this Wednesday morning, if my formula for moment is WL squared over 8, what's my formula for shear going to be? WL over 2. There we go. So for shear, again, so this part, if it's boring or routine, then good. That means you're getting familiar with this. Just make sure that you, again, adjust if your loading conditions change. And then for live load, I think I could do the live load in my head because that's 24 over 2, which is 12 times 3 is 36 kips. What about the dead load? I'm probably not that good. I might need some help on that one.
I got 13.2.
13.2. Do I have a second? Yeah. Okay, good. So finally, VU, again, 1.2, V dead, plus 1.6, V live, 1.2 times 13.2 kips, plus 1.6 times 36 kips. And what do we get for that?
$60.24.
Say it again.
60.24.
Do I have a second? I got something different.
I was 73.
Yeah, I got 73.44. Was it 1.32 maybe? Like if the decimals are there. Did that do it?
I multiplied the dead load by 0.2.
Ah, that'll do it. It's usually something small, so no biggie, no biggie. Now, before we leave this step, so this step we're primarily doing the strength limit state structural analysis, and so I want to leave this step with 3 quantities. I want to leave it with the factored moment, the factored shear, but something else, something that we didn't need before. Say it again?
CB.
CB. We need our CB quantity. Now, the cool thing about this problem is that, so moment, gradient, modifier. So the cool thing about this problem is we are dealing with a situation that looks like this. So we've got a simply supported beam, and we've got a distributed load. And we know that we are provided with braces at the ends. That's our situation, okay? And the cool thing about this is that the CB value, and you can actually derive this, is independent of the span length or the load. So all you have to do is look up our CB value. So more often than not, we're going to try and employ our tools of looking up CB when we can. So if you remember, we can go to table 3-1. We can actually look up our CB values. And so what is CB for this scenario? 1.14. And if you remember, one of the things I said is that this is going to be a low CB value. And so this is what I mean. Low CB values are like 1.1, 1.2, something like that. High CB values are things like 1.7 or 2 or something like that. And by the way, if your CB value is getting over like 2.6, 2.7, something like that, there are a couple instances where that might happen, but you might want to check your math. Like it, that's really high. So, okay, so we're leaving this step with our CB value and our MU of 440.64 foot kips and our VU of 73.44 kips. That's what we left this step with. Okay? And so if you want another name for this step, that is the strength limit state, okay? So now what we need to do is we need to assess our service limit state, and we need to compute required IX. And one thing I'll say about this is that it is possible on a homework or an exam that I might give you a problem and say there is no deflection limit. And so this could be a step that you just skip and just don't worry about checking deflections. Don't worry about selecting a shape based on moments of inertia. So that's sort of why I separate this into its own sort of situation. So we need to compute our limiting deflection, which for this problem was L over 360. Again, that's a really common deflection limit for floor elements in buildings. So we have 24 feet over 360, but we like dealing with deflections in inches. So when I take 24 times 12 over 360, you get 0.8. I'll do that for you. And then for our deflection, to actually compute the deflection, the live load maximum deflection, it is 5WL to the fourth over 384 EI. So all I'm doing to actually compute the required moment of inertia is I'm just sort of swapping these two. So swapping the moment of inertia over here and the deflection over here and plugging in this for the deflection. So it's actually a pretty straightforward calculation. So I would say that IX required equals that. So again, all we're doing is just a switcheroo and plugging and chugging. So a big fraction Am I forgetting something?
17.
There you go. And so now we're leaving this step with a new design parameter, which is
the L is supposed to be to the fourth, right?
Oh, yep, that's right. 0.1 on the mistake count for that. But again, I'm allowed up to 7 mistakes per semester, but I'm the one who's keeping track of it, so it's a corrupt system, I know. All right, so anybody got a moment of inertia for this one? This one, a little bit more involved on that.
We got 965.3.
965.3 and units.
Inches to the fourth.
Inches to the fourth, right? Do I have a second?
Yeah.
Okay, good. Okay. And one of the things I will say when you're doing these problems, and I mentioned this actually in a capstone meeting a little earlier, but one of the strongest tools is your gut. I mean, think about the moments of inertia that we've been looking at for W shapes. If you do this calculation and you get some weird number like IX is 0.0032 inches to the fourth, something's wrong. That's not right. And so use your gut to see if you can, why am I getting the wrong answer? Okay. All right. So now we get into what I would call the really new stuff with discretely braced beams. And that is to select a trial shape. So 3, we're going to select a trial shape. And in order to do that, we're using table 310. Okay. Now remind me, okay, so whenever you're going into table 310, you go in on the x-axis with what? LB, okay? So what is your LB for this problem again?
24 feet.
24 feet. Now on the y-axis, what do we go in on? No. MU, what do we do to MU? We divide out the effects of CB. So on the y-axis, we go in with MU over CB. And I'll call it MU max over CB, just to match what's in the notes. And then there's a reason why I format it that way. So 440.64 foot kips divided by the CB value of 1.14. Okay, and so what does that equal? 386.5. For and that's probably right. I would say for what we're doing here, this is probably one of those areas where you could be a little fast and loose with your decimals, because how you're going to use table 310 is you're going to find that line on the axis, and it's not going to be that accurate anyway. So what we need to do is we need to go into table 310, and we need to find the point where on the x-axis it's 24 feet, and on the y-axis it's 386.5. So we need to zero in on that point, and then remind me what we need to do. We look up and to the right, and what are we looking for? The first solid curve. And remember, the reason that we're looking for the solid curves is because within that region, the solid curves are the ones that represent sections that are the lightest. Okay? So there's no real magic to it. It's just within a given region, as you start tracing upwards, if the curve is light, then it's plotted with a solid curve. If it's heavier than, or if the section's heavier than the next one, plotted with a dash curve. So, I mean, you could pick a dash curve if you wanted, but it's not going to be as economical as the next solid curve. So, I'm curious if anybody has found a shape that we ought to consider.
A W18 by 76.
Okay, a W18 by 76. Now, first off, help me out. What page are you on?
3-118.
So the first thing I would say is if you're not on that page, let's make sure that you're on that. But this is the point right now where I want to make sure that everybody is able to find that. If you're not able to find that, tell me. That's okay. I'm totally willing to come around and walk everybody through that. But I want to make sure that everybody can see that that on page 3-118, there's that point. If you trace upward and to the right, you find the W18 by 76. Is there anybody that's having a hard time finding that? Everybody able to find it? Everybody good? Okay. So I think that's probably the trickiest part of this aspect. Okay? So everything else I think you're going to find is very, very similar. Okay? So first off, the next thing we're going to do is just check the moment of inertia requirements. So IX required was again 965.3 inches to the fourth. What is IX for a W18 by 76? What is that? $13.30, okay? So what does that mean? Somebody help me out. What does that mean? Means we're good. This design is not going to be governed by deflections. It's going to be governed by either moment or shear. Most likely moment, because shears never really govern designs all that much in building design. So I'll say, therefore, section will meet the deflection requirements. So from here on out, this is going to be really simple. Or really straightforward, I would say. Let's analyze the W18/76 and verify its capacity. Now, can somebody make a comment about the beam's self-weight?
Less.
Less than what?
What we had assumed.
Okay, so let's elaborate on that. So we assumed in the design phase a self-weight of 100 pounds per foot. Okay, the beam has an actual. So we assumed 100 pounds per foot. The beam has an actual weight of 76 pounds per foot. So it's lighter than what we assumed. So I would argue that if this section has adequate moment capacity based on the MU we already computed, we don't need to update that MU. We can just go with it. Okay, does that make sense? We don't need to update our loads. Now, we would need to update the loads if the beam was heavier. We picked a W36 by 150 or something. So, okay. All right. So let's analyze the 18/76. Now, if this is a discretely braced beam, you tell me, how do we analyze it? Let me guide this a little bit. How do we determine the capacity of a discretely braced beam? We use this, right? So help me out. If this is our means of computing capacity, you tell me, how do I compute the capacity of a W18/76? What do I do? I need to find LP and LR. I need to figure out what zone I'm in, right? So what is LP and LR for a W18/76? Let's look that up. So what is LP and LR? So 9.22, 27.1. And somebody remind me, what was LB?
24.
So what does that mean?
Zone 2.
Zone 2. And again, for most discretely braced beam designs, you will be in zone 2. Most of them you will be, okay? So if you're not, what I would say is if you're not in zone 2, check your math. I'm not saying it's wrong, I'm just saying check your math. So, all right. So in order to compute the capacity according to zone 2, so here's our flow chart. So in order to compute the capacity of zone 2, remember that's that linear region, we're going to need a few things. We need CB. Do we already have CB? Got that. That's 1.14. We need PMPX. We need PBF. We got LB. We got LP. We've got that. So we need 3 terms. We need CB, that, and that. So let's see what we got here. So CB is 1.14. What is BMP for the W18/76? $611. We have BBF. That's the slope of that line in that linear range. The beam factor. What is that?
12.8.
12.8. And while we're at it, while we don't need it for the LTB capacity, let's compute, or let's look up PVN. What is PVN? for this shape. $232. All right. So therefore, so what I'm doing is I'm just going off of my flow chart here, and I'm saying, okay, so VMN, the capacity, is the minimum of these two quantities. So I'm going to compute this one up here. So let's go ahead and do that. So I've got CB times VMP minus VBF LB minus LP, and so that equals 1.14 times 611 minus 12.8 times LB is 24 feet minus 9.22. Clear that up a little bit. So that's 611. So what do we get for that?
I got 480.87.
480.87. Do I have a second? So therefore, phi mn is the minimum of CB times all that whole, basically everything we just computed, or phi mpx. That I can do better than that. Bless you. I woke up this morning, my eyes were itchy, and I went, yep, it's spring. Let's break out the Claritin. So, minimum of those two is pretty obvious, 480.87. So, to be clear, what we're doing is we're basically saying phi mn is 480.87 foot kips, and we are comparing that with MU. MU is, what was MU? Not MU over CB, MU. 440.64. So that MU over CB, that was just so that we could use the design aid, but that's not the actual moment that's on the beam. The actual moment on the beam, appropriately factored, is 440.64 foot kips. So, therefore, we are okay. And if you want, you can compute a performance ratio for moment, and I'll go ahead and do that for you. You get 0.916. Or 91.6%. So that's not bad. And while we're at it, we could go ahead and say that VBN is 232 kips, and our VU, I mean, what was VU? I think it was like 73.4. And that's obviously okay. And we can get a performance ratio for shear, and again, it's really tiny, 0.317. We know that the deflections are not going to govern, so I'm going to go ahead and just forego the formal deflection check right now because I kind of want to introduce the next lecture. But I think we all know what the answer is. That's the answer. The answer is that design works. Does anybody have any questions? Hopefully this is pretty routine. Like, I think what I have found in steel design is that this stuff is not very difficult, but it's coming near the end of the semester. Everybody's like, Dr. Mike, we're ready for summer. Am I off? Am I
No.
off?
No, you're right.
Nah,
You're right. You nailed it.
Now, I know. Now, I want to at least show you this false positive thing. I talk about it in more detail in the lecture, but I just want to show you the issue, okay? Does everybody have this? All right, let me at least kind of set the stage for this next lecture. And so, like I said, I'm going to skip a lot of this stuff here. But in general, the way discretely-braced beam design works, you go into this table with LB and an MU over CB to select a section, analyze it for shear moment deflections. There you go. Okay, I'll talk about this in the video next time. But I kind of want to talk about false positives and this thing with high CB values. So real quick, I know we're getting short on time, but I want you to follow along with me. I want to conduct an exercise with you. I want to pick a section. I just want to go into table 310. I want you to help me out. I want you to pick a section for the following data. So let me show you what I got here. I've got some random MU max, a moment of inertia, CB, and I've got LB as 20 feet. So what do you go into table 3-10 with? You go in with 20 feet on the x-axis, and you go in with 510 on the y-axis. Somebody help me out. What section is that? Say it again.
W24/84.
See, that's the one I got. Does everybody else see that? Okay. All right. Now, I got another question about the W24/84. So let's say that's your section. Can somebody tell me what phi and P is for that section? $840. Does everybody else see that? All right. Now I'm going to stop for a second. I want everybody to look at the slide. Take a look up here. Does anybody see a problem with this data? Does anybody see a problem with this? Exactly. That's exactly right. Okay. Take a look at this. All right. So here's the problem. The maximum MU for that problem was 1020 foot kips, but the maximum possible FEMN is 840. Remember, the plastic moment, that is the largest capacity that you can get out of a steel beam or that you can count on for design purposes, right? Period. So what happened is we went in the table with MU over CB, but we had a really high CB value. We had a CB value of 2, okay? So the trial section that we picked out of that section was no good, okay? I won't have to call her back. So that led to a false positive. So I'll call you back. So CB serves to increase, so this led to a false positive. The moment gradient modifier serves to increase FEMN, but it doesn't increase FEMN past the plastic moment. But the problem is when you go into table 310, you can't account for that cutoff. It doesn't really work. So you're going into FEMN or into table 310 with this reduced moment that may not reflect what's actually going on. And so the way that you have to handle that is you have to iterate. Now, what you end up doing is this. So if you go into table 310 and you end up picking this shape, because this is the one you all just did a second ago, right? This is the W24/84. So how does it work? Watch this. You just pick the next one. And just keep picking the next solid section until you find one that works. And so what you end up doing if you have a larger CB value, is you just set up a table. Like here's MU, here's the FEMP. It's no good. Like it's not going to be any good. There's no point in doing the math. So if you wanted to check the moment of inertia, you could, but who cares? Because this section doesn't work. It doesn't work, right? So then you would do is you'd go to the next solid section. Look up its VMP, it doesn't work. Go to the next section. Look at its VMP. Oh, okay, now we have a section where VMP is larger than the applied moment. So this is a section that's at least worth checking. This is the point where I would actually take a look at the moment of inertia. Now again, we still don't know if the W30/90 is going to work, but it's at least a worthy section to check and see. Then what we would do is check the moment of inertia, and now we see, okay, the moment of inertia is worth picking. And if we found that this was no good, we would just abandon all that whole chart and just go to table 3.3. So what I have is I have an example where I go through a high CB value problem, and we go through this process. We have to actually iterate it quite a few times. So the other thing I'll say when you watch the slides is that be prepared for some back and forth, because you're going to have to turn to table 310, turn to table 3.2, turn to table 310, turn to table 3.2. You have to do that a lot. I can't really get around that. It sort of is what it is. I stole a minute from you, my apologies, but I will see you all on Monday. And if you have a chance to help